Thank you very much, Professor Ayu. This is a joint work with my colleague, Professor Saito and Watanabe. One of the important issue in cloud physics is that the size of the droplets. For example, this is the laboratory experiment data, which was conducted by Professor Shaw at Michigan Tech. So, for example, the number of aerosols is not large, then distribution of the size of droplets are quite wide. But when the droplet number, the aerosol number is increased, then the peak of PDF becomes moves toward the smaller size, and the width of this distribution gets narrow. The same trend was observed by our cloud turbulence simulator. So to describe this distribution of the droplets in cloud, so we usually use two kinds of the equations. The one is the evolution of droplet radius. The time derivatives of R square is proportional to the supersaturation. Supersaturation is a kind of the key quantity in cloud physics. And also the supersaturation fluctuates in space and time. And quite often the Rajban model for the supersaturation is used. Here, tau t is the turbulence characteristic time. The tau c is a phase relaxation time of the supersaturation, describing the time of the condensation or evaporation and so on. And there is a random fluctuation. So with this set of the equations, we can derive the Fokker-Planck equation of the radius of droplets, and we can argue the aerosol number dependency on the of the PDF or something like that. Another important issue is the liquid water content power spectrum, which was measured at the mountain top of German Alps. So, for example, this is a frequency, and the power spectra of LWC obeys the f to the minus 5 at low frequency, but at some frequency, it deviates from this curve. The slopes look like the f to the minus 1. So this slope has some resemblance to the Bachelor spectrum in the passive scalar in the viscous convective range, where the spectra used to obey k to the minus 1. But the precise physics of this spectra is not known. Also, some people predict that the existence of two kinds of the k to the minus 5 range of supersaturation or LWC spectra. So there are many efforts, but so far, to my understanding, so the clear explanation of this kind of the spectra in cloud is not given. So our target here is that to describe or to understand the spectra of supersaturation in cloud, which is characterized by the incident time scale, phase relaxation time. And the point is that the phase relaxation time is independent of wave number. For this purpose, we consider two scalars, supersaturation and LWC. For example, we consider a cloud over the sea, and we consider small domain inside the cloud. So inside the cloud, we assume that the mean scalar gradient. And since our this parcel is very small, therefore the inside of this part, we first approximation, all the fluctuation is statistically homogeneous and in a steady state. And we consider no nucleation and no collision, no coalescence occur. And for simplicity, we assume that the mean of supersaturation is 0. And there is a uniform gradient along the vertical direction. The first quantity is a water vapor mixing ratio, which obeys the convective diffusive equation with the term describing the condensation rate and effect of vertical uniform mean gradient. The second equation is the liquid water mixing ratio, QL. But again, we have the condensation rate term. And the second term describes the fallout effect of the droplets from the graph. So the QL quantity and the CD is, they are described in this way. It's a sum of the cubics of droplets or sum of the radius times supersaturation. The supersaturation is given by this equation from QV. So anyhow, point that QL and CD carries the properties of the particles. But our target is to derive the spectra of supersaturation. Therefore, for this purpose, we'd like to have some continuum representation of the LWC and the CD condensation rate. For this purpose, we introduce a local spatial average over the size of delta volume ball. So result is that the continuum representation of the LWC is expressed as the product of the number density of droplets times the cubic of R. And also, the rate of change of the LWC by condensation evaporation is, roughly speaking, expressed in terms of product of supersaturation times QL. So with these two equations, and we now change of the values from QV to S and from QL to phi. We assume that this phi is very small when compared to the other quantities. So our equation becomes now supersaturation, which has this term and LWC. However, the product of phi and S is very small, therefore we discard. And also the dropout effect are discarded for simplicity. Now, the point is that the tau S is the phase relaxation time of supersaturation, which is given by the product of mean number density of droplets and mean radius. These are purely determined by the thermodynamic nature of the system and independent of wave number. Therefore, our target is that the spectra of supersaturation, which has some inherent characteristic time. Now, our set of the equation is as follows. The velocity turbulence field is excited by random force, and U excites the supersaturation, and supersaturation excites phi. So this consists of chain of excitation. However, for simplicity, in the following, we consider only the spectra of this equation of supersaturation. We assume that the turbulence field is homogeneous isotropic for simplicity. Now, our equation is here. And we can construct the equation of the spectra of supersaturation in this way, some way. The point is that a transfer function, the Ts comes from this term, okay? And the point is that this transfer term contains some turbulent transfer time scale. Here, tau k is characteristic wave number dependent turbulent time scale. And one important point is that it contains also wave number dependent Damkira number, which is the ratio of the tau k to phase relaxation time, tau s. This is the key quantity. Okay, this is a schematic picture of time scale. This is the wave number and the tau. As you know, that in the inertial convective range, the turbulence characteristic time obeys k to the minus 2 decaying and to staying some value and the decay quickly becomes short. For example, we consider tau s. So with this tau s, there must be some wave number ks at which Damokela number is 1. Therefore, for low wave number range here, Damokela number is much greater than 1, meaning that tau s is much shorter than the characteristic time of turbulence, which means that in this dynamics, this term balances this term. Therefore, result is that we have this balance from which the supersaturation spectra obeys k to the minus 5 But this means that the supersaturation is directly excited by the turbulence field. It's just a copy of the turbulence field. However, the wave number around here, where the Damokela number is much smaller than 1, therefore, the convex term transfers the supersaturation fluctuation in a usual way. Usual way means that the Overhoff-Poisson type cascade process works here. Therefore, we have usual k to the minus 5 spectra. C is Overhoff-Poisson constant. But also there is a third regimes. Consider the tau s very short, and accordingly, also there is some, we can consider the wave number range that tau k is comparable to tau s. So in that case, we are considering short time tau s. What's happened around here? So around here, the velocity field, it can be approximated by the locally linear field of velocity coordinates. So the u is approximated by linear function of x. And this convective term balances with the relaxation. The result is that the modified Batchelar spectrum. Modification means that we have this term. Okay, if dk, that means dk means that the ratio of the Kolmogorov time to the phase relaxation time. Dk goes to 0, we have Batchelar spectrum. Now, the following is that our numerical verification of the supersaturation spectrum predicted by the theory. For the existence of two kinds of k to the minus 5 so we need some wide range of wave number. So direct numerical simulation would be difficult. So to make the story or analysis simpler, we start with the shell model. The shell model is that a skeleton of Navier-Stokes in the wave number space. So interaction of the wave number band n is very local in the sense that the band n interact with n plus 2, n plus 1, n minus 1, n minus 2. The same is true for the supersaturation. So here is the phase relaxation time and excitation. We integrate the set of the equation. Then we have this plot. In this plot, all the kinetic energy spectra, scalar spectra, multiplied k to the 5 But in the case of the kinetic energy, there is some intermittency correction. Therefore, compensated spectra follows this way, slightly negative slope. Similarly, the passive scalar supersaturation in the sense that 1 over tau s equals 0, no effect of the phase relaxation, usual passive scalar. When compensated by the k to the 5 thirds, curve goes to this way. I don't know why this have this positive slope, but anyhow, in this point, so that we use this line for the zero effect of phase relaxation. And this is a turbulence kinetic energy spectra for the reference. Now we consider the case 1 over tau is 0.01. Curve goes this way, and at this wave number, curves tend to leave this line and tend to be parallel with this passive scalar supersaturation case. When the 1 over tau s becomes 0.1, curves goes to this way and again depart, and they tend to align to be parallel with the ES. So these the trend seems to be consistent with the previous the theoretical prediction, meaning that two kinds of the k to the minus 5 cell range exist. For example, we draw the line of tau s equal 100, and this line crosses the characteristic turbulence time tau k at this wave number. Okay, at this point, this line tends to leave the energy spectra. Or tau s equal 10, this line crosses here with the tau k. Again, this line leaves the kinetic energy spectra and aligned in parallel to the passive scalar. So this observation seems to be consistent with the previous physics in theory. The same is true for the passive DNS, but the wave number range is very limited in some way. As you can see that the one more moment. Okay, this is a compensated kinetic energy, and this is compensated passive scalar without effect of the phase relaxation. But the tau s becomes finite and shorter. You can see low wave number tail of the spectra of supersaturation tend to align with the kinetic energy. This trend seems to be consistent with the previous physics. The same is true for the high wavelength number simulation. The same. So far, the DNS or shell models and the other physics and the observation are consistent with the previous theory. Finally, supersaturation spectrum for the very high short supersaturation phase relaxation time and short value of Kolmogorov time. So when decay becomes larger and larger, so the spectral slope becomes so steeper. This is also consistent with the DNS. So let me conclude my talk. So we studied the spectra of supersaturation. And wave number dependent Damkira number is very important, which controls the supersaturation spectrum. Thank you very much.
Do we have any questions? Yes.
Interesting presentation. If you go 2 slides up when you talk about the DNS and you show the spectra, the K, the spectra versus K delta, one up.
This one?
Yeah, this is one of them. At the
or maybe
end, yeah, this one, exactly.
Yeah.
At the higher end, you seem to have accumulation of energy, right? That upturn.
Mm-hmm.
That would indicate generally that the resolution is not the DNS resolution because you accumulate energy. You have to go to scales that are much smaller than that to get a spectrum that falls down without the overturn. Can you please comment on that?
I didn't follow you. I mean, are you saying that this part?
Towards one?
Yeah, the high wave number content, the optic.
This one? All right, you're right. This is okay. Our wave number is limited. Therefore, there are always, even in this far diffusive range, both the kinetic energy and the scalar energy are transferred to high wave number range, but there is a finiteness. But by the nature of the DNS, so which conserve the total kinetic, conserve the energy by the convective term. Therefore, the constant the flux tend to pile up here. So this part, I think that this is irrelevant to the present physics. Did I answer you?
I don't think I would call this DNS. I would call that unresolved DNS. That's what I would call. As soon as you get this accumulation, the pile up of energy, that means you're not going to the smallest fluctuations that you will be able to get should there be DNS, right? I think you
I understand, but if we have the infinite the power of a machine or infinite resolution, we hope that the curves of spectral curves should go this way. For example, if you have plenty of the, if you decrease the Reynolds number, we don't have this kind of the pile up of the energy. Therefore, if you admit that there is some effect of the pile up the energy around here, and some effect, but there may be some effect at the small scales. But in that sense, so the small scales are not dissolved. So the simulated field is not exactly the equal to the actual one. But that is, the context here is not to see this part. So the point in this DNS is that whether the k to the minus 5 to k to the minus 5 third range exists or not. So for that purpose, I think that this behavior is enough.
All right. We have time for one more question.
Mm-hmm.
The droplet size spectrum, that's a droplet size distribution is a different point than what you're showing, but its evolution is known to depend on details of the droplet size distribution. So, but I don't have an intuition about how the supersaturation spectrum depends on or is sensitive to initial conditions. So maybe you could comment.
You were right. So for example, if we do this kind of the simulation, the initial distribution of the PDF of the droplets may have some effect, but the supersaturation, I think that the key quantity to control this change of the PDF is just roughly speaking that the time scales of supersaturation is a key, and also the number of the droplets. So the details of the supersaturation, I think the is not how do you say maybe a second effect.
Thanks, Professor Gotoh.
Yeah.
With the interest of time, we would like to proceed to the next talk, but before that, let's give our speaker another round of applause.
Thank you.